we're now finally ready to move on to the concept of angular momentum. And the concept of angular momentum is very useful. It's used in stuff from all over the place, from bicycles to spaceflight to gyroscopes, etc. And the reason it's so useful is because in angular momentum, you can have really a lot of momentum without it going places and flying and hitting things. Because after all, if you want a big weight to have a lot of momentum, you have to get it going at a high velocity. Big mass, big velocity. But you could do the same thing by spinning it in a circle. Now we have a disk with a big mass, and we're spinning it with a high angular velocity, omega. And as a result, it has a lot of momentum, but it's very self-contained. And because it has so much momentum, it's very resistant to change. So that's why your bike wheels don't like to tip over, and why gyroscopes don't fall. And this allows a lot of useful behaviors. But first, before we can engineer stuff around that, we have to be able to calculate it. So we go through the same steps as before in this. First, we calculate the original angular momentum. Then, you go ahead and calculate the final angular momentum. And then finally, you set them equal and solve for any variables you're looking for. And by doing these three things, we can solve almost any related question for this. So let's start with an example question so we can see how we go through those steps. So imagine we have a merry-go-round spinning. And the merry-go-round spinning at some angular velocity, we'll say 1 radian per second. That's actually spinning pretty fast. It's going around every 2 seconds. It'll make a complete revolution. Sorry, every 2 pi seconds, it'll make a complete revolution. And there's a kid playing on a tree overhead. And the kid drops down onto the merry-go-round. And first we should figure out, is the merry-go-round going to speed up or is it going to slow down? And when we think about it, the kid has no angular momentum. His angular momentum is 0. The merry-go-round has some angular momentum. We'll call it L. When they fall and combine together, the net angular momentum has to be constant. You can't create or destroy momentum. So 0 plus L is still going to have to equal L. But the merry-go-round now can be thought of as having more mass. Now it's a disk with some mass m1 and a point with some mass m2. And because it has more mass, it's going to need less angular velocity. So as a result, we're going to go from having angular velocity omega 1 down to angular velocity omega 2, where omega 2 is less than omega 1. So by falling on this merry-go-round, the kid's going to slow it down a little bit. And if we throw enough stuff onto the merry-go-round, we could get it slowing really, really slowly. So now they figured out that it is going to slow down. Now we're ready to actually calculate it with numbers. So let's say the kid is 20 kilograms, and we'll say the merry-go-round's 50 kilograms. And as we said before, it's spinning at 1 radian per second. So what's our initial angular momentum? Well, for the kid, he's not spinning, so the kid is 0. And the angular momentum for this is going to depend on the radius, which we'll say is 1 meter. Plugging this into the equation, we end up with 25 kilograms radians meters squared per second. I'm not going to write this out in the future. We'll remember that that's our units for angular momentum, but it's a real pain to write out. So we'll just add it back in at the end and only add together terms that are angular momentum. So let's keep a little track of that, but it'll still be easier than writing it out. So now at the end, the moment of inertia of this object is 1/2 mr squared, which is 25, and that's in meters squared kilograms. And then that's plus the mass of the kid and his distance. So he's 20 kilograms, and we'll say he's also 1 meter out. So that's another 20 meters squared kilograms. So now the moment of inertia of this is 45 meters squared kilograms. Now we know that the final moment of inertia is angular velocity times moment of inertia, and that has to equal the original angular momentum, which equals 25. So we divide through by I. We end up with omega equals 25 over 45. And I realize I miswrote that up here. And 25 over 40 is 5.555 repeating. So that is the new angular velocity of the merry-go-round. It looks like I did that backwards. It should be 0.55 repeating, so less than 1. And now we have to fact check to make sure that makes sense. Does 0.55 radians per second make sense? So we do the math. We know it should be spinning more slowly. 0.55 is less than the 1 radian per second that it had before. And as a result, that makes sense. That's a good speed for it to be spinning at. And this doesn't seem that complicated, and it really isn't. And the reason for that is we just followed these instructions exactly. First of all, we figured out our original. Then we figured out our final. And then we set them equal and solve for variables. And this is the same technique you use for any problems, whether they're very simple or very complicated. You just go through and you solve for what you can, and as you do that, you'll build a more complete picture of what's going on, and eventually you'll be able to calculate exactly what each thing's doing. So hopefully you understood that. If not, maybe go back, rewatch this video. If you did, you're ready to move on to problems. Good luck.